I'm going to walk you through our cooling curve lab. At each station there were two chemicals, A through G, I think it was. And at this station we have chemical G with its mass written there, and this looked like is chemical E with its mass. So you just had to pick one of these. I'm going to pick this one, chemical G, and I'm going to note the mass, 17.20 grams. And I'm going to record the initial temperature, which is 89 degrees, 88.8. It's hard to focus, so I'll just read the temperature out. That's my initial temperature. Is 88.8 degrees. I'm going to move that guy over to the ice water bath and record every 10 seconds. And I'm doing this, I'm working by myself, so I gotta try to keep the bulb submerged in the liquid without touching the sides of the test tube. So I was 78. I gotta make sure the chemical's fully submerged under the ice bath and my thermometer is submerged under the chemical without touching the sides of the test tube. So I'm already at 58. This may not be regular increments because I'm working by myself. Yeah. I had to add more ice, and while it was doing that, it's still at the 32, and we can see that it's already starting to solidify. It went up a little bit, maybe because I keep taking it out. So we're still at 33, and solidified pretty good. And now it's dropping to 27. Now it's dropping pretty fast. $23. So there was a plateau there at 33, 32, and now it's under 20. It's at 19. And it's just going to keep dropping because it is solid. Here's the thermo data I provided for you. We're going to use the data for sample G to calculate the change in enthalpy from the initial to the final temperature. I copied my data. I'm going to make a rough sketch of a heating curve, or in this case, a cooling curve. I'm going to plot the temperature on the y-axis, and that had units of Celsius, and I'm going to put time on the x-axis, and that was in units of seconds. Now, on a heating curve, we normally put Q on the x-axis, but that's really what was changing. So I'll put Q there, although we were measuring time. Now, the highest data point is close to 90, or a little below 90, and the lowest value is a little lower than 20. So I'll make increments from 20 at every 10. So that's 30, 40, 50, 60, 70, 80, and 90. My initial reading was 88.8, so that's a little bit under 90. I made 12 readings, so I'm going to put about 12 increments on the x-axis. And actually, you can forget the units of seconds. And we're assuming I recorded these at equal increments, which I obviously didn't, but I wasn't far off. So my first reading is right there, around 88.8. My second reading is 78. So that's about there. My third reading is at 58. So that's about there. And then it's at 42. Then at 34 and a half. And then at 32. And then I get another one at 32 and 33 and 33 before it drops down to 27, 23, and then down there. So that's what my cooling curve looks like. So the melting point, or the freezing point of the substance, you could say is 32 to 33 degrees. Let's go with 33 degrees Celsius. The heat added or removed from the system went to the phase change rather than a change in the temperature. Your post-lab question is to calculate the Q, or the delta H, of your experiment. So in this exothermic process, how much heat was lost by the system from its initial temperature to its final temperature? So we're going to break this up into 3 steps. Step 1, we're going to go down this leg of the journey, and we're going to use Q is equal to MC delta T. The mass of my sample was 17.20. And here was the thermo data provided for substance G. So the specific heat of the liquid, which is where I started it, is 2.1 joules per gram degrees Celsius. The change in temperature for this liquid phase is my final temperature, which is right there, 33 degrees, minus the initial temperature, which is where I started, was 88.8 degrees. That's negative 55.8. So the heat released through the first leg, which is the decreasing in temperature of the liquid phase, is right there in joules. I'm going to convert this to kilojoules by moving the decimal over 3 times to the left. So negative 2.02 kilojoules is how much heat that was lost during that leg of the journey. Now let's find out how much heat was lost going through the phase change. To get that information, we need the heat of fusion for substance G, which is given to us as 33 kilojoules per mole. Now we need to convert grams to moles using the molar mass before we can use this enthalpy of fusion. So I'll do this in green, the heat released during the phase change. My sample had 17.20 grams of substance G. The molar mass is given to you. And then we can use that heat of fusion. And don't forget to turn that sign to negative. You can use all positive numbers while you're doing your calculations, but just make sure you switch the sign at the end. And this number is in kilojoules, negative 2.18. So that's how much heat was lost in the phase change. Finally, we can see how much heat was lost in this third leg of the journey. And we have to use a specific heat value for the solid form of the substance, which is different from the specific heat of the liquid or gas. So it's 1.7 joules per gram degrees Celsius. The change in temperature in the solid form is our final, which is 19, minus the initial part of that journey is, at the melting point, is 33. That's going to be negative 14. The heat released during the cooling of the solid phase is negative 409 joules. I'm going to convert that to kilojoules by moving the decimal over 3 places to the left, so all my units are in kilojoules. The final step is to add up all the Q's. And let's turn that sign negative. By the way, I didn't use my stored numbers, so I could be a decimal off. And I didn't pay much concern to sig figs. And because delta H is equal to Q at constant pressure, you can also say this is equal to Q.